Howdy class. So now we are starting chapter 10, which is all about energy. So it starts with energy and energy changes. So we're gonna do like an intro and then get deeper into this energy thing as it relates to chemical reactions. So typically we write our chemical reactions, as you know, reactants on the left, products on the right. Uh, that's the that's all we knew so far. Reactants become products, but that doesn't really tell the whole story. For many reactions, energy, often in the form of heat, is absorbed or produced. So you can think of some chemical reactions that probably absorb or produce uh, heat. And that would be like if you light a fire or something. That fire is going to give off heat. It's going to keep you warm. So we don't usually write these in our chemical equations, but it kind of is involved. Like it's very important. So if energy is absorbed um, for the reaction, that means energy has to be added for the reaction to even start. So um, energy acts like a reactant in that case. So this example of solid water, otherwise known as ice, melting to turn into liquid water requires energy. And you probably already knew that because if you hold an ice cube in your hand, it's going to melt and turn into a puddle in your hand and probably all over the floor too. So the heat from your hand was absorbed by the ice cube and it melted. So that's not actually a reaction, as you should know. So maybe not the best example, but this is a physical change. But it's a good example to show you to get started here. And then other reactions, energy is produced. So the energy acts as a product of the reaction. So this is a combustion reaction, the combustion of hydrogen gas. So when we mix hydrogen gas and oxygen gas, we make water. This is also, as you should know, a combination reaction, in addition to being a combustion reaction. And it's also a redox reaction. This has all of the good stuff in it, actually. This reaction is awesome. And you've already seen it too, because I played a video in one of my lecture videos of the hydrogen balloons. When you light them on fire, you get a nice big explosion because the hydrogen gas in the balloon mixes with the oxygen in the air, and we get this explosive reaction where energy is produced. So these are the two types of reactions. Either energy is absorbed or energy is produced. And almost very, very unlikely are there going to be reactions where energy is not absorbed or produced. So for now, you can imagine that probably most reactions either absorb or produce energy. Energy is involved in some way for these chemicals to rearrange, for these atoms to rearrange, I should say. And we have a term for this. This is called thermochemistry, the study of how energy, specifically heat, is involved in chemical changes / reactions. So chemical changes are chemical reactions. So a more broad term is thermodynamics, and thermodynamics studies the relationship between heat, energy, and work, and converting between those three things. And we'll talk more about that a little bit later. But when we're talking about chemical processes, chemical reactions, it's useful to define the system, which is the item or items or reaction slash reactions that are happening. So the things of interest, I would say, and the surroundings, which is everything else, literally everything else. So everything outside of the system that can exchange energy and or matter with the system. So these are a couple examples here. This system is, I'm not actually sure what this reaction is. To be honest, I should have probably looked that up, huh? But there's something in a beaker that is, giving off this gas, this smoky fume, and the beaker where our reaction is occurring is our system, and then everything else is our surroundings. So we are giving off both energy, most likely, and matter in the form of these molecules, these gaseous molecules that are getting out. We're giving off energy and matter to the surroundings in this case. A more general example is, the Earth. If you want to include everyone in the world and everything in the world as part of your system, you're being very magnanimous, and I don't know if that's how you say that, magnanimous, and you are, thinking of the Earth as a whole, and everyone in it is, part of your system, then everything else is the surroundings. And it might not seem like it sometimes, but there is a lot else out there. The rest of the universe is the surroundings. So technically, in this case up here, the rest of the universe is also the surroundings. But like your book mentions, we typically are only considering the immediate surroundings, like maybe our chemistry lab room as the surroundings. We're not talking about like the rest of the universe, really. We don't need you to measure temperatures or pressures of the rest of the universe, just your immediate surroundings. And there's a little bit of a designation here that is kind of important, is thermal energy versus heat. So thermal energy is a static property of the system. Thermal energy is the energy related to, motion of molecules inside a system. So thermal energy at one point in time, while heat is the transfer of thermal energy. So heat is a transfer, not a single state. All right, so there's two types of processes, like I said. We can describe these with more scientific terms than just energy is absorbed or energy is released slash produced. We call those endothermic or exothermic processes, respectively. So an exothermic process is where heat is transferred from the system to the surroundings. So that's like your fire. You have a little fire here. I don't know, I'm not very good at drawing fire. And it's giving off heat. You can warm up your hands, or you can make some s'mores. Let's roast a marshmallow. So it's your campfire. So this is exothermic. It's given off heat. Heat is transferred from the system. The system is going to be, this reaction here, the combustion reaction. Heat is transferred from that system to the surroundings. So like to you and your marshmallow. The temperature of the surroundings increases. So like when you sit closer to the fire, you feel warmer. The temperature of you, in that case, you are the surroundings if your fire is the reaction. So the temperature of the surroundings increases when we have an exothermic process. An endothermic process is where heat is transferred to the system from the surroundings and the temperature of the surroundings decreases. So we have a really good example here that we started with, actually. Gonna draw a little hand here. Don't judge my hand. It sort of looks like it has a thumb. And this is an ice cube. Gonna make it more cube-like. I don't know. That's making it worse, isn't it? But that's your ice cube. And it's melting. So it's gonna like drip off of your hand. I promise this is just like an ice cube and not, I don't know, a flesh wound. This is water. Drip, 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 drip. So when you hold the ice in your hand, like we said on our first slide here, the ice is melting. So it's absorbing heat from your hand in order to melt. So the ice is our system. It is absorbing heat from your hand. Your hand is the surroundings in this case, and the temperature of the surroundings decreases. If you're holding an ice cube, your hand's going to get cold. So, you know, that is our relationship here. If you're putting your hands, you know, kind of near-ish a fire, your hands are going to warm up. If you are holding an ice cube, your hands are going to get cold. And your hands are the surroundings in both of those processes, and exothermic versus endothermic. If we want to talk about, you know, specific chemical reactions, we have a couple here. So this first one that we talked about on the first slide, the combustion of hydrogen gas. So we are mixing hydrogen gas, like in our balloon, with oxygen gas in the air when we light it on fire. And we're making some water. That's a combination reaction that we're making water. This is an exothermic reaction, as I told you before. So the heat is given off by the system. So note, with an exothermic process, heat is given off by the system. Heat is transferred from the system to the surroundings. And when we have an exothermic process, that means that the initial state of the system, so our hydrogen gas and oxygen gas, have a higher energy. This arrow indicates the energy than our products. So when we have a higher energy in our reactants than our products, heat is given off by the system. And we have the opposite here with the decomposition of mercury oxide. So mercury oxide requires heat in order to decompose. This is kind of like one of our steps in the copper cycle, if you remember back to lab this week. So this mercury oxide absorbs heat. So heat is absorbed by the system. This is our system, the mercury oxide. Heat is absorbed by the system from the surroundings. The heat comes from somewhere. It comes from the surroundings. And our decomposition reaction occurs. So in an endothermic process like this one, the initial state of the system, the mercury oxide, is lower in energy than the final state. So we are increasing in energy, so we need to absorb that energy from the surroundings. Whereas over here, we're going from a higher energy to a lower energy, and we give off that heat to the surroundings because we don't need it anymore when we go to a lower energy. This should look kind of familiar to the energy of the photons that we saw before, when electrons would go from higher energy levels to lower, or vice versa. All right, so this should look familiar because I had a slide pretty much exactly like this way back in chapter 3 when we first started talking about energy, and then we were talking about energy related to photons. Now we're talking about energy related to reactions. So energy is measured in a few different units. Like if you buy heating fuel or an air conditioner or whatever, you'll probably see BTUs on there. Food energy is your calories, food calories. You'll see on nutritional labels, of course. And then the energy that we care about in this class is the energy of chemical processes, which is usually given in joules. Joules is the SI unit for energy, or sometimes it's given in calories because calories have a pretty useful definition, as we'll see down here. But just a refresher, a joule is equal to the energy possessed by a 2-kilogram object moving at 1 meter per second. And this is our definition of joules using our other SI units to break it down. And then calories. Calories are going to come up a good amount in our, or at least they'll be related to things that we're going to talk about a lot in this here chapter, because 1 calorie is the energy needed to raise the temperature of 1 gram of pure water by 1 degree Celsius. So that's going to mean a good deal to you in a couple sections here. In particular, the section that Nick is going to teach you. Surprise, that's going to happen next week, so get excited. So a calorie is related to raising the temperature of water. And a food calorie is equal to 1 kilocalorie. So note, food calorie has this capital C, whereas our chemical calorie has the lowercase c. And 1 calorie is equivalent to, or defined as, 4.184 joules. And this little equal sign with 3 lines means that it's an exact conversion. So I know you guys really love sig figs. And this is a reminder for you that an exact conversion, whenever you do an exact conversion, you don't have to consider, or you shouldn't consider, the sig figs of the numbers in that conversion factor, because they are exact. You can imagine that this has like a billion zeros after it. It's so exact. And same here, 0.000000000. These are exact conversions, just like 1 milliliter equals 10 to the negative third liters. That's an exact conversion. So are these. 1 calorie is defined as 4.184 joules. So that one, you don't use 4.184 joules. You don't use that for your sig figs. It does not tell you that the thing, the energy you're talking about has 4 sig figs. That is an unlimited number of sig figs in that number because it's an exact conversion. Okay, that's enough harping on exact conversions. And these are some useful conversions between all of our different units. So you guys can use this as needed, but you might not need it. So yeah, it's just there for you to see all the different kinds of energy units, and some are really big, some are really small. Cool. We're probably only going to need to convert between, like, I don't know, those 4 probably. We're not going to talk about BTUs or watt hours. I think those are watt hours. So we're not going to talk about those, but we will talk about joules and calories and sometimes kilojoules and kilocalories. All right, so I'm going to stop here actually and start with 10.2 in another video.